Good morning, everyone. Come on in. Anybody have any questions while everybody's coming in? Remember, hopefully y'all did your test last night. You got another one due Wednesday.
Yeah, about the test real
Yes.
quick. You know, it's underneath the nothing category in grades, meaning it weighs nothing.
Yeah, okay, I'll fix that. I didn't realize that was that. I thought I'd said it, but anyways, that's not a problem. It takes about 2 seconds to do it.
Okay, cool. And
do it after class. If you don't see it by next time, let me know. That means I forgot it.
I gotcha.
And that's test 4, right?
Yeah.
Thank you. I just wrote it down. Hopefully I'll remember. Is there another question you had too? Anyone else?
I was going to ask if chapter 11 and 36 were due last night.
The chapter 11 what did?
If chapter 11 and 36 were both due last night.
Damn it. I don't know what happened. I definitely didn't set it to be didn't mean to set it to be last night. I wonder if I went back and when I was changing stuff, I might have. Sometimes when you use the roller ball and a mouse, if it's over a box, it'll change the dates. That must have been what happened. I will fix that. Whoever did it, like if y'all stayed up, I'll look and see that y'all got it done early, and I'll give you some extra credit points for it. But otherwise, I'm going to open it back up. We have finished chapter 11, but and 36. No, that was right. That's what I had. Yeah. I was thinking you were talking about 14, but no, that's definitely was what I attended. But just remember, you guys got also if you do it today, it's only like 5% off or 3% off. So if anybody missed it, make sure you get it. But yeah, you certainly had enough time to do 11 and 36. Sorry about that. I was misthinking when you told me 36 and 11. The 11 threw me off. I was thinking that was the chapter we're working on right now, but yeah, we're on 14. Oh, it stinks to get old. My brain just stops working. The only thing I remember anymore is numbers and how to do calculus. It's like calculus and trig. That's pretty much my total skill set now. Anybody have any other questions? Yes, chapter 11, chapter 36, and test 4 were all due last night. That was sort of the bad side of me giving you so much time on your test. They basically put a lot of different things due in one day. So keep an eye. As far as I know, the mastering homework deadlines are all right. I will double check again today, and if I find anything amiss, I'll let you know, and I'll change it, and then I'll let you all know. But I think they're good. We should finish. I think we might finish chapter 14 today, but if not, it's going to be one more day. If the due dates aren't consistent with that, I'll change them. How about anyone else? Anyone else have questions? All right, so I recommended you do this the other day, guys. The Taylor series and Mclaren series expansion. Specifically, I said you should do the Taylor series expansion on sine, cosine, e to the x. And I said it would really be good if you did 1 plus x in parentheses raised to the n power. That gives you the a binomial expansion, which comes in quite handy in physics. But I thought I'd give you some of the results, because you'll see once you realize how easy it is to actually do it, and then you do it, you'll see like a clear pattern that's going to make it easy for you to remember the results. So let me go ahead and turn on my document cam. Remember, the Mclaren series is supposed to be that any f of x that meets certain criteria. Again, most of our functions do meet such criteria, so in physics, so shouldn't be a problem with that. There you go. F of x is equal to the summation from I equals 0 to infinity of 1 over I factorial, and then the ith derivative of f evaluated at 0 times x to the ith power. Okay, that's it. And by the way, today is 11, 15, 21, and this is PHY 241D01B. So I have that. All right, got another student coming in. So when you actually take the time to do this, what you'll see is it takes about I think it's 4 is the pattern. Like once you do 4 derivatives, you start repeating yourself. So when you evaluate the derivatives at 0, you're basically getting like 0, 1, 0, -1, or 0 or 1, 0, -1, 0, and then it repeats itself. So that's what makes it so easy. But in so doing, you get sine theta is equal to theta minus 1/3 factorial theta to the 3rd power plus 1/5 factorial theta to the 5th power minus 1/7 factorial theta to the 7th power plus 1/9 factorial theta to the 9th power minus ... I think you probably could see what was going on from that point on, actually, but I went ahead and carried a couple extra digits. So that's sine theta. Notice all these powers are odd, and notice how this matches this, and even this one, which is 1, that would be 1/1 factorial. So they're all actually the same as the exponents. And notice that the sign reverses. Okay. Not only am I giving you this because I want you to do that Mclaren series expansion, but we're going to make use of it today. Now, the other one, since they're all odd, by the way, that's why sine has an odd behavior. So odd meaning in the mathematical sense, specifically sine looks like this from 0 to 2 pi, but it looks like the negative of that from -2 pi to 0. So if I take sine of x, negative x, that's equal to the negative of the sine of x. That's an identity that you use, but you can see now why, because obviously if I go to a mirror reflection of this point, that would be right here, and that's the negative of it. But you can see now why that's the case, because it's an odd function. Again, odd function means when you replace the argument with negative x, you get the negative of the argument with the positive x. Now, cosine theta is quite nice as well. Cosine theta ends up being 1. And then when you do the next term, notice only the evens are going to exist. So I go 1, and then I go negative. Actually, I think this one was actually positive, if I remember correctly. I actually just did it. I should have just pulled out the paper, but here we are. So yeah, let me pull out the paper. I'll just double check, make sure I don't want to. Yeah, cosine does alternate signs as well. So it's 1 minus 1/2 factorial theta squared plus 1/4 factorial theta to the 4th minus 1/6 factorial theta to the 6th power and plus 1/8 factorial theta to the 8th minus ... Now, here's where you're going to see why I actually took the time to verify that it was alternate, because here's the e to the I theta, or e to the theta, excuse me. E to the theta is 1 plus theta plus 1/2 factorial theta squared plus 1/3 factorial theta cubed plus 1/4 factorial theta to the 4th plus ... So you can see it's really just having no sign changes whatsoever and including all the stupid terms. Okay. So with that, you should be able to now easily take this and substitute it for e to the I theta. In other words, everywhere you see a theta, put I times theta. And basically every power of theta, like, or excuse me, every power of I is like I1 or negative I or -1. So you see I to the 1 power is I to the 2 power is -1, I to the 3 power is negative I to the 4th power is -1 times -1 is +1, and then I to the 5th power. Now that would be 1 times I, so that's just plain I again, because I to the 4th is 1. So we're back to I. So you really only have to do 1, 2, 3, 4, 5, and you start repeating yourself. So what you'll have every time is either a term that's I, or a term that's -1, or a term that's negative I, or a term that's +1, or back again to I's. And when you do it, when you set it up that way, you'll see that a certain number of terms always have I in front of it, and the other terms always have a plus or minus 1. And from that, you can actually piece together, or plus or minus I as well, you can actually piece together and get Euler's formula. So give that a try. Any questions on that? Again, that's just a little bit extra math. It's one of those things that we repeatedly used in this course, but I never took the time to do it. So every time they did it, it sort of confused me. So I just didn't want you guys to have as difficult time as I did. So I'm really, really, really encouraging you to do that. In fact, if you do it, I'll give you an extra homework grade. So it'll be an extra credit homework, meaning if you don't do it, nothing's going to happen. But if you do it, there's going to be another homework grade that'll be dropped. So try for extra credit. That means you have to do all of these. I would say go to the first 9 non-zero terms. Whoa. Terms for each. And that may sound like a lot, but like I said, as you saw here, it only took 4 to start repeating. The same thing with sine and cosine. The derivatives only take 4 to start repeating. So, all right. So let's go ahead and get started on the new material, which is still chapter 14, but now we've done the harmonic oscillator, and the harmonic oscillator gave us this really nice differential equation. It said d2x over dt squared plus, in this case, it became k over m times x is equal to 0. That caused us to choose x is equal to a cosine omega t plus phi, where omega was the square root of k over m. And of course, omega is also equal to 2 pi f, and f is 1 over t. So t equals 2 pi times the square root of m over k. So all these things are the important results, and they're going to be that way anytime you have a constant in front of the x that's this. Okay, so now let's look at a simple pendulum. Now there's a couple ways you can do this. I like to do it with the torque equation. Pendulum. Evidently, I also don't like to be able to spell the word pendulum. So anyways, with a simple pendulum, you might have a little bit of ceiling right here, and you've got a cord out at an angle theta from the vertical, and the cord's length is L, like this, and you've got a mass M hanging on it. Well, from the free body diagram, I think you can see, well, actually, I don't even need to do a free body diagram. What I need to do is take this and realize this force is mg, and that's the actual part of the force. Part of that force is the actual force that's going to make the or apply a torque to the thing. So we're treating this thing right here as if it's an object, the string ball system as an object. So if I wanted to put a torque on that, if I actually applied a force right here, I would take the component of it that's perpendicular, and then that component times this length would be the torque. So the summation of the torques is equal to I times d2 theta over dt squared is our Newton's second law for rotation. Now, the moment of inertia for a point object out at some distance L from the center of rotation is just ml squared. So that makes that part pretty easy. And what I get for my torque is, notice when theta increases, this force actually pulls the other way. So they actually have to be related by a negative, just like we did with F equals negative kx. So I'll get the force is mg sine theta. And then I multiply that by the lever arm, which is the L. And the reason why I'm doing this is, notice this triangle. Since this angle is theta, if I drew a vertical right here, this angle would also be theta. And then, of course, since this angle and this angle are vertical angles, that one would be a theta as well. So you get that this part is mg sine theta. So that's where that came from. Everybody follow that? So I'm taking the component of torque that's perpendicular to the lever arm, which is, what torque is. Torque is R perpendicular times L, or it's L perpendicular times, oh, excuse me. I don't know why I said L. Or it's F perpendicular times R. We used F perpendicular times R, so life was really sweet. So now that I got that, I almost have something. What I really want to do, though, is finish out this equation, and then I'm going to divide by some things to make the constants look a little better. But I got negative mg sine theta times L, that's the torque, and that's got to equal ml squared. Remember, that's the moment of inertia for a point object, basically going in a circular orbit L distance away from the center, and that's d2 theta over dt squared. So you can get d2 theta over dt squared. Pulling this to this side will become plus mg L sine theta. And all of this divided by ml squared, because that's what I did to make this one. And that equals 0. And I think you can see this 2 is going to cancel out with that guy, and this mass is going to cancel out with that guy. And I got d2 theta over dt squared plus g over L sine theta is equal to theta. Now, that is a nasty differential equation. In fact, you have to use a very specific type of integration to solve it. It's elliptical integrals. So we don't want to do that. But if we remember correctly, I've just finished telling you guys that sine theta is actually equal to theta minus 1 over 3 factorial theta cubed. You can see that if this angle is small, think of it in radians. If this angle is like 0.1 radians, then this angle would be 0.1 times 0.1 times 0.1, or this term would be 0.1 times 0.1 times 0.1, and then divide it by 6. Well, 0.1 times 0.1 times 0.1 is 1 over 1,000. So it's 1 over 6,000 compared to 0.1. This term is teeny compared to that term. So as long as you keep your angles small, then we can assume sine theta is equal to theta. So for small theta, sine theta is approximately equal to just plain theta. And now I've got d2 theta over dt squared plus g over L times theta is equal to 0. Notice this is exactly the equation we had for the mass on a spring. We had a second order derivative in some variable, in this case x and t. Ours is theta and t. We had a constant, or plus a constant times the top variable. Well, we've got a constant times the top variable, and then we got equal to 0. So from that, we know that theta is going to be equal to theta max, because we figured out that that A turns out to be the maximum amplitude. So you might as well just call it theta max, like it's the amplitude, times the cosine theta of omega t plus phi. And just comparing the two, the omega in this case was the square root of this quantity. So the omega in this case must be the square root of this quantity. So omega is equal to the square root of g over L. But that also means, since omega is equal to 2 pi f, that means that f is equal to omega over 2 pi. So it'd be 1 over 2 pi times the square root of g over L. And then t is equal to 1 over the frequency. So you can say this is going to be 2 pi times the square root of L over G. So these are all new results that you can use. And of course, if we give you initial conditions like at t equals 0, theta was 12 degrees, okay, and we released it. Well, that's just code word for theta equals 12 degrees at t equals 0. And then the other one's code word for d theta over dt equals 0 when t is 0. Okay, so you can do boundary conditions or initial condition things like we did before and figure out what the phi is and the theta max is. I think you can automatically guess what the theta max is, but that's the key point is now you can do that. So let's do an example of a problem where we can sort of make use of this stuff. So let's say example 1. Anybody have any questions on that before we start? So some geologists are trying to find oil and other below ground deposits. So they make a, let's say, let's say L equals 26.43 centimeter pendulum. And determine its frequency to be 0.97. So I'll say frequency equals 0.9705 hertz. These are just the numbers I made up. So that's the problem. What is G? At their location. So this is an actual real life thing you can do. You can use the period of a pendulum in any particular location to determine G. That can sometimes, for instance, be used to determine your altitude, or it can sometimes be used to determine what's below the surface. Like if you have something that's a little less dense right below the surface than rock, then maybe that's going to make your G a little smaller. If you have something more dense, maybe it'll make a G a little bigger, that kind of thing. So this is a problem, and we're just going to try to use what we just learned about the simple pendulum to find out G. So can anybody guess which one of those equations might be most helpful to use? Anyone? Yeah, I see it. Okay. I think y'all are just being shy. Or whatever you call it when you're grown up. You're not answering questions. Okay. So if we look, we see that F is equal to 1 over 2 pi times the square root of G over L. So if I square both sides, that tells me, and multiply by 2 pi, that gives me 2 pi F squared is equal to G over L. So I can finally just say G is equal to 2 pi F quantity squared times L. So in this problem, I'm going to say that G is 2 times pi times 0.9705 hertz. And remember that cycles per second, or yeah, I guess we'll just use it like that. That's going to be squared. And then I'm going to multiply that by 0.2643. It's got to be in meters, of course. So now you'll get meters per second squared. And the 2 pi is actually used to convert the hertz, the cycles, to radians. That's one way of thinking about it. So now you've got radians per second squared. So that's radians squared per second squared times meters. So that gives you meters per second, which is exactly what we want. And when I do this calculation, y'all should verify it yourself, but I actually wrote it down earlier, so I'm just going to give it to us. It's 9.827, and I carried one extra sig fig, meters per second every second, which you could also write meters per second squared, of course, but I like to still think about it that way. So notice we're using sig figs here, and that's really what you should do when you're just using numbers to solve problems. As a first order approximation, just use your sig fig rules, and that should get you, keep you from making too bad of a mistake. But it's also helpful to go ahead and carry at least 1 or 2 extra digits. So if you have to do something more precise, then you can use error propagation formulas or stuff like that. So in this case, we got 9.827, or 9.828 is the acceleration due to gravity, a little bit higher than what we use, 9.80. So there's probably something under that particular part of the Earth that maybe is a little denser and therefore has a little bit more gravitational pull, at least close to the surface. So any questions on that one? All right, well, now let me jump to another topic, which is very closely related. And this topic is going to be the physical pendulum. Okay, so with a physical pendulum, this is what you basically have is a blob of any kind of random shape, if you will, which looks like it might be one of those, what are they, nerds, the little candies with the little purple guys for their logo. So anyways, if this is the point at which it's pivoting, and this is, say, the center of mass, so this is the center of mass right here, then this distance from here to here is going to be labeled as h, and this angle right here is going to be labeled as theta, and let's say it has a mass m. Okay, so with this one, we again get the summation of the torques is equal to I times d2 theta over dt squared. We're going to say this thing's just some object and it has a moment of inertia I. In fact, this experimental setup is one of the ways we can determine the moment of inertia of an object. Okay, so this is our object. It's tilted at some angle theta. Obviously, the force on it's going to again be, or the torque on it's going to again be mg sine theta times h. And of course, that's negative because when theta increases, the force is going the opposite way. So with that right here, we're going to say negative mgh sine theta is equal to just plain I times d2 theta over dt squared. So we're going to divide both sides by I and then put them all on the same side, and we'll get d2 theta over dt squared plus mgh over I times the sine of theta is equal to 0. And as you might guess, that sign makes it ugly, so we're going to assume small angle. Okay, so we're going to do that. Now, the big deal with that is, by the way, your book mentions, I think it said at 15 degrees, sine theta only differs from theta by 1%. So a good rule of thumb is as long as you don't want to, off by more than 1%, then keep it smaller than 15 degrees. And I've actually found when we measure periods of rotation or period of motion in the lab, we've gotten up to like angles of 60 degrees, and it's only been off by a couple percent. In terms of the period. So you use the period of a pendulum and you determine that period, and then you find out the formula that we use from this only differs from the answer we got experimentally by a couple percent. So it really is pretty surprising how far you can go till you get there. But anyways, now that we've done that, we're in a position where we can actually make the differential equation in the way that we like it. So we're going to say d2 theta over dt squared plus mgh GH over I, who almost wrote an L there, over I times theta is equal to 0. So that just looks exactly like the harmonic oscillator we had before, which was d2x over dt squared plus, was it m over k? Yeah, it was k over m, sorry. K over m x is equal to 0. So we again can say this implies theta is equal to theta max cosine omega t plus phi, and omega has to be equal to the square root of mgh over I, and of course force is equal to, or excuse me, friction. Force and friction is what I said. What's that? The frequency is equal to omega over 2 pi. So we're going to say 1 over 2 pi times the square root of mgh over I. RT, which is 1 over f, is equal to 2 pi times the square root of I over mgh. Okay, so these are all new facts that we can use for this new type of problem, which is called a physical pendulum. Okay, so this is the physical pendulum. Okay, and our new facts are theta equals theta max cosine omega t, including the fact that omega is equal to this. We also have this, and we also have this. So again, new expressions. So let's do another example. Example 2. A cylinder of mass m and radius r is hanging as shown. What are omega, f, and t? Okay, so what I'm going to do is I'm going to imagine a cylinder. Okay, here's the center of mass, which is out basically a distance r from the edge. And what we're going to do is hang it from right here, and it's going to pivot about an axis pointing straight out of the page like that. And this distance will be 7/8 r. Okay, and of course this angle again is theta, and we're going to assume a small angle. So with that in mind, I will say, okay, well, I've got to figure out the moment of inertia of the cylinder. Well, I know the moment of inertia of the cylinder about its center of mass, which is right here, by the way, is equal to 1/2 mr squared. But I know the parallel axis theorem suggests that I is just going to be 1/2 mr squared plus m times 7/8 r squared. Okay, so now I know that I is actually 1/2 mr squared plus 49 over 64 mr squared. So this could be 32 over 64. 32 plus 49 would be 70, 81. So it's 81/64 mr squared. I'll leave it like that, even though that's an improper fraction, but it's kind of nice because you can see when I added 32 to 49, I think I got 70 plus 79 plus 2, which is 81, which is another square. So I really kind of like that, right? Because that might work out to be something nice. So now I know the omega, according to our last calculation, is just equal to the square root of mgh over I. So it's the square root of m times g times 7/8 or 7/8 times r, by the way, divided by 81/64 times mr squared. And this pen might be dying. Let me try another one. Okay, so you can see this m is going to cancel out with this m. One of those r's is going to cancel out. But basically what I'm going to get is the square root of 64 over 81, which is beautiful, times 7/8, which is a pain in my butt, times g over r. So we could actually call this would be 8/9 square root 7 g over 8r. So all that's acceptable. I'm going to call that omega, and I'm going to box it off of the red box. Okay. Now, technically, that 8 down there shouldn't remain, because you can make that into 2√2, so that'd be 18 down in the bottom, and then √7/2. So that would be a little neater, and that's what your typical math instructor would require you. I wouldn't take off points if you did a written test that way. But anybody have any questions on how I did that? So now I want the f, and the f, of course, is supposed to be 2 pi over omega, or excuse me, omega over 2 pi. So the f would equal 8/9. Let's go ahead and do it with the fancy way. Let's say 2√2 down here. So that 2 is going to drop off of that. So that actually makes it a little better. It'll be 4√9. So I'm going to say 4 over 2 pi times 9 times the square root of 7g over 2r. And of course, we can make other substitutions like that. 2 could cancel out with the 4 up here and give me a 2 over 9 pi. So I could say 2 over 9 pi square root 7/2g over r. So that's a more succinct, or perhaps even prettier version of f. But that's what the frequency is. If I actually gave you numbers, of course, you could calculate what that would be. But the main thing is I wanted you to see how to actually implement this and how to use a parallel axis theorem for something, fairly mundane. Now, finally, I want the period, and the period is 1 over f. So the period is actually 9 pi over 2 times the square root of 2r over g. Notice this is meters per second per second. So it's in the bottom. That means it's going to be seconds, second squared, in other words, on the top, over meters, and that's canceling out with the meters in the r. So it actually does give you unit of time, and that was the easiest form of the equation to see it. That's why I waited till then to address it. I had already worked it out, of course, so I knew it was right, but still. Any questions on that one? Okay, so that's a.
Sir, could you zoom in on the last line there, the two things you squared? I can't quite see.
Okay. Let me.
So what is that? Frequency is 4 over 20 times 9?
4 over 2 pi times 9. Sorry about that.
And then 7
g over 2r. And then of course I factored out that 2 and canceled it out with a 2 and the 4. And that gave me 2 over 9 pi times 7/2 G over R under the square root.
Okay, I think I got everything. Thank you.
No problem. All right, so that's another typical problem that you can do, and you can see how the beauty of the just knowing the harmonic oscillator problem, which is any second order derivative, and you'll see in a second we're going to add another term with a first order derivative and a constant in front of it, and a 0th order derivative with a constant in front of it, and that's going to be the harmonic oscillator as well, but that will be the damped harmonic oscillator. So let me start off by looking at that as follows. Let's say we have mass on a spring. Actually, yeah, I'll hang it from a ceiling instead of push it off a wall. So I've got this spring like that. Then I hang a mass on it and it stretches. Okay, and I give it a little bump and it starts to oscillate. Okay, so according to Newton's second law, the summation of the forces is equal to m d2x over dt squared. We're not expecting the masses to change, so that's why I didn't worry too much about using dp dt instead of m d2x. So in this case, the forces are going to be negative kx. Again, remember, if you set up a coordinate system such that this is x, when x gets bigger, the force actually points in the negative direction. So that's that. Also, if the thing is moving with some velocity this way, an air resistance or a fluid resistance force would point in the opposite way. So I'm going to say minus b times dx dt. Normally we take the stuff and just write bv right here, and that's fine, but I figured why not? We can just write it as velocity as a derivative. And that's equal to m d2x over dt squared. So rearranging, what I'm going to do is divide by m and divide by, well, we'll see first. Let's divide by m, and we'll get d2x over dt squared plus, putting everything on the same side, everything's going to become positive, plus b over m times dx dt plus k over m x is equal to 0. So this is the more general form. Notice I now have the second order derivative represented, the first order derivative represented, and the 0th order represented. So again, we're going to use our typical scenario, which is we make an on-site solution. So in this case, they do a kind of weird thing. I don't really like doing it this way, but what they're going to do is they're going to say, let x is equal to, they're going to again have a amplitude, which they'll call a, but they'll just assume that you're going to know that it's going to have a exponential decaying term in front of it. And they're going to call that, which normally what you do in a calculus class is you just give it some value like rho, and you just turn that in as a solution, right? And you plug it all in, and that works out. But they're going an extra step in your physics book, and are going to say it's times cosine omega prime t plus phi. So they still got those two potential constants of integration, if you will, or initial condition things to be determined, and that all works fine. But you can see it's a little more complicated when you do this. Okay, you actually have to do chain rules and all that, or multi-product rules when you go to take derivatives and stuff like that. So let's do that. So dx dt is going to be, it's always just going to have an a in front of it because that's just the constant amplitude basically. So if I take the derivative of e to the negative gamma t, I'll get negative gamma e to the negative gamma t. And then I didn't take the derivative of cosine this time, so that's just cosine omega prime t plus phi. Now I've got to take, leave this one and take the derivative of that one. So I'm going to say plus e to the negative gamma t times the derivative of cosine, which is of course negative sine, which actually I should leave a space there. Sorry about that. So you know when I take the derivative of argument, I'm going to get negative omega prime times derivative of cosine was the negative and now the sine omega t plus phi. So that's the whole derivative. It's not pretty, right? And we can't really do much with it in terms of simplification. So we're going to now just take the second derivative, d2x over dt squared. And when we do that, we're again just going to keep this a out in front. And actually, I think we're going to run out of space, but we'll have to spread it over a couple lines. So I'm going to take the derivative of this first, and then this. So I have two terms for this one, and then I'm going to do the same thing over here. I have two terms for that one. So this will be a 4-term thing. So I now have a negative gamma that's already there. And now I'm going to take the derivative of e to the negative gamma t, and that's going to give me a negative gamma squared e to the negative gamma t times the cosine that's already there, omega prime t plus phi. Now I've got to do the other part of the product rule, which will be plus, still the negative gamma t is there, or excuse me, negative gamma is still there, times e to the negative gamma t. Now I got to take the derivative of cosine, and the derivative of cosine, of course, is negative sine, so that's going to be a negative omega prime sine omega prime t plus phi. So that's just the product rule for the first two terms. Now I've got the product rule for the second two terms. That's going to be the derivative of this one, which is negative gamma e to the negative gamma t times the plane function, which we already have, negative omega prime sine omega prime t plus phi. Now I've got, in addition to that, I've now got to take the derivative of this term, but leaving that one. So I'll put this here. It'll be still e to the negative gamma t. Now I got to take the derivative of this, which I'll put this negative omega out in front. Derivative of sine is cosine. So I get cosine omega prime t plus phi. And then the derivative of all this gives me that. So I'm going to get a, that should be actually just omega prime squared, not the negative squared. So I'll put this like this, and I'll just say a negative 1's in there. I think that works. Okay, and that's the whole kit and caboodle, which you can see is just wonderful. It's going to be so much fun to work with us. So let me put all this junk out here. I got negative gamma squared is just going to be positive gamma squared. So I'm going to say gamma squared. I'm going to leave the a out in front of everything. So I'm leaving the a off right now. So that's omega squared, or gamma squared, excuse me, negative gamma t cosine. Since the argument's always the same, I'm just going to leave that instead of writing omega prime t plus phi, because obviously there's no loss of information there. Y'all can tell what it's going to be. And then this is going to be minus gamma times e to the negative gamma t times negative omega. So I'm going to change this to positive, and I'm going to put the omega right here. And then times the sine. Again, same argument, so I just put that there. So that takes care of that term and that term. Now I'm going to do this term, which would be a minus gamma. So I'm going to say minus gamma e to the negative gamma t. This is times negative omega prime, so I'll make that plus, and I'll put omega prime here again, just like I had there. And now I have a sine again, same argument. And now I have this guy, which is a -1 times e to the negative gamma t omega prime squared in this case. The negative's already been taken care of, cosine. Again, just the argument of cosine. Now that's just the first term. That's just first derivative, the second derivative there. That's the first term of this equation, and that's what I've written out already. So I got 4 but ugly terms already from just that. Now all of that's going to be times a, so I got to put an a here like that. Actually, I'll put it in the square bracket. Now I've also got to do b over m times dx dt. So that's another 2 terms. So I'm going to say plus b over m. Now the 2 terms that I get here would be negative gamma e to the negative gamma t cosine function. Now this one will be minus omega. So I'll say minus e negative gamma t omega prime sine, again, of the argument. So I've got that. So that's my second term. Now I still got the x term, which is just k over m. So I'll say plus k over m times what we said our derivative would be, which is, oh, this a is out for everything. So I have to put that like that. So k over m times the a I already got, e to the negative gamma t cosine argument again. That kills off that, and that kills off that. And all this is equal to 0. So that's not fun, but it's in some sense is doable. Now, here's the problem. We've got to now find basically a way to get out the sines and the cosines and set them in some sense equal or factor them out like we did before. Remember when we did this before, basically we had what we called a characteristic equation. It was an algebraic equation multiplied times e to what would be e to the, or a times e to the negative gamma t times cosine, but we just didn't have the e to the gamma t in there at that time. You can still get that way, and you'll get a characteristic equation. And it turns out the characteristic equation dictates that gamma is actually going to have to be b over 2m. Okay, so I think this method is not very good. I suggest you look at my method on YouTube channel. But that's what one of the equations is going to dictate. And the other equation is going to dictate that omega prime is equal to k over m, square root k over m, minus b squared over 4m squared. So that's really all you need. You need to write x is equal to a e to the negative b over 2mt times cosine of square root k over m minus b squared over 4m squared t plus phi. Now, of course, the derivative of that in time is the first derivative is the velocity. The second derivative is the acceleration. And of course, omega is this. So you can get from omega, you can get f. And from f, you can get the period. So there's all new equations that you can use. But we got a new complex system. And in fact, you have to evaluate different terms. But I think by doing it this way, like your book likes to do, it obscures why you get all the different terms. Okay, so technically our time's up. I'm gonna I might just record another one today where I'm gonna just let a equal e to the rho t and see that you naturally get 2 solutions, and it'll make a little bit more sense. But basically what happens here is the 3 ways you can answer it is it can get something like this as one of the solutions. They call that underdamped, and what it is basically like a cosine function with its amplitude exponentially decaying. Another one you can get is one that decays way too rapidly, And that's because the b squared over 4m is basically really close to are very close to k over m. When you get that one, that graph tends to look like this. Right. And then the other one actually is oddly, it's just a linear function times e to the negative gamma t. So it sort of goes like this and just falls off that way. So you get overdamped, critically damped. Critically damped is when these two are equal to each other, and it basically makes it where you don't have a sinusoidal term at all. You end up having a 1 plus let's say mt times e to the negative b over 2mt. So that's really what the critically damped is. And then you have underdamped. He's in the couch. On the couch, I should say, underdamped. So the underdamped is that blue curve like that. The critically damped is really just a linear function that looks linear for a little while because the e to the negative b over 2mt is essentially 1 for a very small value of t. And then eventually what you're going to get is it'll start to decay rapidly and it'll become an exponential as opposed to linear. So instead of going all the way across like this, it just dies out. So anyways, that's the 3 responses. The only thing we haven't done now for chapter 11 or 14, excuse me, is the damped harmonic oscillator with a force on the other side. I'm going to leave that as one. I might talk about it in class next time. I'm not sure. But you can, of course, look at it on my YouTube channel. So I think it's going to be fair game to do one where instead of having this homogeneous form where it's 0 over here, you can have like a cosine function or a sine function as a forcing thing. And it's just, your book just gives you the solution and you can just use it for homeworks, but I'm not going to test you on it. So we're done with chapter 14. If anybody has any questions, you can stick around. Otherwise, you are free to go. Thank you for coming, everyone. Tyler, if you haven't left yet, I will open that back up, but I have to give you a penalty for any late tests. So that goes for everybody, I guess.
Okay,
well,
thank you.
it does go to everybody, but anybody else? Randall? All right. Well, y'all have a good one, folks.